So the last thing we studied last time is the voltage current feedback. Anyone can tell me why I call this a voltage current feedback, this circuit? Do you remember? It's a part of your exam. Right. Since eraser. I have current in, voltage out. Then why do I call it voltage current instead of current voltage? Yeah, because the input to the feedback amplifier is the voltage. The output from the feedback amplifier is the current. Okay, because when we're talking about feedback, we care about the feedback amplifier. So when talking about voltage current, remember to look at this. I repeat many times already. Don't mess up in your midterm, in your final. Okay. Now, but I also call this shunt-shunt, right? Why it's called shunt-shunt?
Because to measure the voltage, we have to shunt it to ground through a high impedance connection, and to feed current or to take away current, we have to shunt it to ground.
Yeah, very good. So first of all, great. First of all, he said both here as a whole circuit is parallel. So they're shunt-shunt. And he further explained why, how to double check it, because output we are sensing voltage, of course, need to be shunt, parallel measure voltage. Input is to do the comparison, subtract the current or add current, right? Again, need to be parallel. You cannot add current by doing in series, right? So there's shunt-shunt. But what is this shunt? The first shunt refer to where?
Shunt is the input,
The
the amplifier.
To the whole circuit. Yes. The input to the whole circuit. And then the second one is the output from the whole circuit, right? So this is the confusing part, right? So remember when I talk about shunt or series, we look at the whole circuit topology. So this shunt. And earlier we said this is also called voltage current feedback because we only look at the input and output of this feedback amplifier. Is that okay? Then if we agree with this, the rest will be easy. We just reuse what we derived earlier, because when we derived the equation, we did not distinguish whether it is voltage or current. Okay? Even if it is charge, it is okay. So open loop gain is R0, just a name. But R0 is better because this is a trans impedance amplifier. Okay? Then the closed loop gain is R0 divided by 1 plus K R0. It's okay? Yeah. So now let's look at an example, right? Again, the first thing you want to do is spend time. You have very long time in your exam, only 4 questions. So sit there for 5 minutes, really understand what it is before you dive in. What circuit is this? And then what is it doing, right? Maybe you can start. Who want to say something about this circuit? You can start from some very simple. Input is what, output what transistor we have, and then whatever. Like keep brainstorming. Any suggestions?
It's 2-stage.
Okay, very good. 2-stage.
Feedback.
And you see there's a feedback, okay?
And it's a shunt feedback.
Okay, so now you start saying that is shunt feedback, but you may go too fast for others, right? So let's step back. We have feedback, then maybe let's look at where is the feed forward. The source, okay.
And then going into the gate of M2.
Okay. Yeah, very good, right? So he said he see this, right? So now we start formulates to what type of amplifier is this, because we don't want to do small signal. We want to look at the cheat sheet. Do you agree? He said common gates followed by common source, so it's a cascade circuit, right? Very good, right? So anyone have some objection, or you check your cheat sheet and then you try to look at the common gates amplifier. Is it the same as what you learned before? Usually we talk about voltage input, right? So good. So you do not just copy the equation right away, right? But indeed it's common gates. But also before we discuss a case when the input is not voltage, it is the current. right? So some of you might have that in the cheat sheet already also, right? But it's good. So basically what I see is I have a current go into the common gates, get amplified, and then it will amplify one more time by a common source, and then I have a feedback, right? But because my input is current, output is voltage, so what type of amplifier is this? So it's a trans impedance. Very good, right? It's a trans impedance. And you also see that it is a common gate followed by common source, right? So of course, some of you already know everything how to solve it, but assume that I'm not familiar with this, then let me try to draw, just to do some sketch. What does it look like if this one has no feedback? So this is VB, and this is I in, right? And this one goes to here. And this is VO, right? Sorry for the drawing, it's not clean, but do you agree with what I'm drawing? This is without feedback. Yeah? Input is current, and then output is that, right? So let's take a look. If we agree with this, right, actually you need to think further, but I believe I'm correct because output is voltage, I sense it, and then through this resistor, I subtract some current or add some current, right? So I think this is correct. So I want to go ahead to find the gain. What is the gain of this circuit? We actually learned before, but we can do it step by step. Let's look at the gain of the common gate. What is the gain of the common gate? Typical is GMRD. Okay, so let's do this, right? I say the gain, right? If you don't have that in your cheat sheet, then you do need to go through this step. The gain of the common gate, by definition, is what? When you say GMRD, and here, which GM, by the way? GM1. When you say it is GM1RD1, what is the definition? Which one, what divided by what when we say gain? V out, maybe let's call it Vx, divided by what? Let's just call V in. It's very important you write this down. Vx divided by V in. Make sense? But we don't have V in. We only have I in, right? How do you find I in? Can you say again?
V over R equals I.
V over R equal to I. So exactly, V in over I in equals to R in. Right. But everyone okay with this? Write down the definition. If you write it correct, you are not doing anything wrong. It's just that, am I able to find what is R in? Maybe you find that you don't know how to find it, right? But the worst case, you just do small signal. You can find R in, right? Because that's learned in E122. Every circuit, you can just linearize it, do small signal, apply V in, find what is the I in, find their ratio, that is R in. Yeah? But in this class, this is R in. You already know that by inspection. What is the R in? Someone say 1 over GM1. Can you explain why? So he said, look into the source of the transistor. I'm going to be very strict and picky. I want you to be accurate. Is that always look into the source of the transistor is 1 over GM1? Only when what? Which one is grounded? VB, very good, VB. Yeah, sorry, yeah, this is VB, But VB is grounded, of course, right? I was asking for VG is grounded. Yeah. But VG now is connected to constant VB, which is grounded in AC, right? Here I don't repeat again, but you always know this already when we talk about the AC response. Ground all the DC voltage, open all the DC current, right? Current source. Okay, so yeah, so you're correct, but I just want you to be specific. And or on the other hand, you can say it is the input to a common gate amplifier, the input impedance. We derive in small signal already. It is 1 over GM1, right? So with this, then what I want to put it as, so this is a little bit, then I'm going to write this. I'm saying, okay, actually I care about the trans impedance gain of common gate, which is Vx divided by I in. Make sense? Now Vx is Vx. Then based on this equation, right? I know that Vx equal to V in times Gm1 out D1, right? Because it's common gate. Vx equal to V in times Gm1 out D1. Okay? So I write this as V in Gm1 out D1 divided by I in. Okay? But we just say what is V in divided by I in. 1 over Gm1. Right? So that got cancelled. So the gain is just out D1. And it should be, the unit should be, because it's transimpedance. Yeah, we are finding the output voltage divided by input current. What confused you? What did I do wrong? What I'm saying is, I showed that Vx divided by I in, this is definition, is the gain of the common gate. And Vx, of course, you know it is V in times the gain of the common gate, right? The voltage, Gm1 out D1. Because Vx divided by V in equal Gm1 out D1. And I also know that V in divided by I in is 1 over Gm1. So just the whole thing becomes 1 over Gm1. Right? This is 1 over Gm1. So Gm1 divided by Gm1, then I have RD1. But some of you may even say, this is obvious to me. This current, right? Now I don't have feedback. So maybe let me draw it again so it's easier for you to study later. And let me do a better drawing. So we have VDD, RD1. This is I in, VB, and this is Vx. And then we come to this transistor. This is V out, right? This is without the feedback. All this current goes to where? It goes through RD1, correct? If there's no channel length modulation. Right? You can think about all the extra. Remember, what is the meaning of I in? It's the extra small signal current. You were biasing this at 1 milliamp for DC. Then I in have 0.0 or 1 microamp going up. It means that the total current becomes 0.999 milliamp going down. Remember, I spent a lot of time talking about the DC biasing. This extra current, you just think that I have less current going down, right? And this less current going down, the less DC total current going down, through source must be equals to the delta of the current through the drain. You still have all the current going from the drain to the source, right? So the I in, the small signal one, must be equals to the current going through RD1. And then what is the change of the voltage due to this change of the current? It must be RD1 times ID, I in. Right? So another way is a good learning is that I can call this method 1. I also can have method 2. Again, this is a repetition. We did that before when we saw this circuit in another class, right? You can think of this. This is VDD. It's grounded. And then this is RD1. Right? And then this is VB. You put into the small signal. I in. Isn't that I also have I in going into the RD? Right? If you just draw the small signal, all the I in will go through RD1. And then what is Vx? Vx minus 0 divided by RD1 must equal to I in. Just Ohm's law. Right? Why this is 0? Because it's VDD, AC ground. Yeah? So as a result, Vx divided by I in equals to RD1. Same. Right? So just for instructional purpose, I have two versions. But you need to really understand. But however, in the exam, if you're so good, you see that already, done. The gain is RD1. Okay? So just treat it as a review. I know I spent a lot of time. But this is only CG, right? So let me call this A, B, right? I know I'm... and then let's do here C. What is the total gain? Total A0 or R0 equals to what for the feed forward? RD1 times. Okay, why it is GM2 RD2? Common source. What is the gain of common source? Minus GM2 RD2. You need to be careful of this. Otherwise, a negative feedback will become a positive feedback. Everything will screw up. RD1 times negative GM2 RD2. This is due to the common source. So it is your negative GM2 RD1 RD2. Is the units correct? It's still trans impedance, right? Because GM times RD is unitless, right? So it is still correct, right? So this is a good way to check, right? So we spend a lot of time just to figure out what is the forward gain, but that is okay. If you are very familiar with this, right? Those guru will just say they can see it already. RD1 times negative GM1 RD2, right? How about the feedback? Now we say this is a voltage current feedback. Again, what is the meaning of voltage current feedback? What is the meaning of voltage? It refers to what? Voltage input to the feedback, right? So look at this. Our feedback circuit is so simple. Let's take a look. Yeah, we need to be careful. So let me just draw it. So this is the feedback, okay? And we know this is V, this is I, right? This is the feedback network. But I need to map to my circuit, which is equal to what? I have V out here, then I have a RF, correct? But now the problem is, where does this RF connected to on the other side?
Well, the current's
Someone say, there's no concern because It will just open, right? And then how about here? Then, and you also say source to the source of this transistor, right? So I do have a impedance going up. You can just draw the whole transistor if you want, M1 or everything, that is fine, up to you. But we don't want to do that. We just want to find the effective resistance. Okay, he said 1 over GM. Do you agree? Because looking up is 1 over GM1. Okay? So my goal is to find what is the I, because by definition, right, the I needs to go in here. So I want to know what is I. Why? Because the feedback factor, by definition, what is the feedback factor? Output divided by input. What output of what and input of what? Output of feedback, input of feedback. I know I'm asking something very simple, but once you know this, you should be able to tell me, just in terms of the symbol, what is the output of the feedback? I. What is the input of feedback? We zero, for example, right? So all I need to find is to find the relationship between I and V0. So how do we find it based on this? Use what? Based on this circuit, how do I find the relationship between I and V, given R, F, and 1 over GM? KCL or just simply Ohm's law? Yeah? Just Ohm's law. So can you tell me what's the Ohm's law that relates I and V out for me? But just give me the equation. I want you to be super careful. One more time. How do you use the Ohm's law for this circuit? Like you are teaching a high school student or middle school student.
Do you mean for the conversion or for the?
I want you to give me the exact correct result, relation between I and V0 using Ohm's law.
V equals I.
What?
Should be equals V divided by GM plus RF equals I.
That is what I want you to. What is the meaning of V for Ohm's law?
The voltage applied relative to the relative to the other node, which we can consider ground sub the out.
So it's not about whether you relative to other node, right? It's the difference of the potential across the element you are interested in, right? So can we do it again? What is the difference of the potential in this circuit? You want to do V out minus 0? Okay. Then what is the current? If you do V out minus 0, right? Just like you tell the kids, I apply 2 volt here, 5 volt here. I expect currents to go from where to where? From the 5 volt to 2 volt, right? If you will to Ohm's law. If you deliberately want to make it troublesome for the kid, you can say, I want to define the current from 2 to 5. But then what do you need to do to the current? You do negative. I keep asking this because we still take it for granted that we usually just say, I see this voltage divided by current is Ohm's law, but it's only correct in magnitude. Ohm's law is that you define the current from node 1 to node 2. If you define in that way, then the current equal to voltage from node 1 minus voltage at node 2. So now what you're doing here, you say, now I want to define the difference from V0 minus 0, then the currents need to go from V0 to 0, correct?
And you're saying that the current should go in feedback.
Yeah, it doesn't matter because I draw the I in this direction. So in that case, then the current is negative I, if you want to define in this way. I is just a symbol. I say that in this direction, I call it I. Okay? Because my definition feedback factor is this. If you don't like that, you say, I want to draw I from right to left, fine. Then your feedback factor by definition is negative I divided by V0. You need to follow all this strictly. But the most important is the Ohm's law, right? Ohm's law is that this, right? I think we should not mess up this anymore. I have a box here. This is called node 1, this is called node 2. When I say V1 minus V2 divided by I equals to R, this I must from 1 to 2. That is the definition, right? For Ohm's law. You cannot say that it is from 2 to 1, right? Same here. If you say this is V0 minus 0 as you want to define in this way, then your current has to be going in this direction in order to get RF plus 1 over GM1. It needs to go in this direction. You can call whatever you want. You call IB if you want. But now I ask you to let me know what is I. Then your IB is equal to my negative I, because I'm defining that way, right? I define that way because my feedback factor will be just I over V0. If you insist to use IB in this direction, fine. Then you put IB here, no negative. But the K needs to be negative IB, because the definition of K is going into this network.
Yeah. Negative I.
VR has nothing to do with the negative to the Ohm's law, right? VR is just a symbol. It can be negative with negative value, positive value. And you can just take positive value to think about it if it is easier. These are just symbol. The important thing is how you do the subtraction. Any questions?
I'm assuming you're going to the strict definition to allow for a simpler case of the feedback loop.
No, which definition you're talking about? You're talking about the definition of I? Okay.
The whole definition. Defining K.
Oh, for defining K is just where one is the convention. Okay, current always go into the pot. You don't need to follow that. But the point is that by doing this, it will be very simple. You will see that it's going in, then it is negative feedback. It's a subtraction right away. If you want to go here, then you are doing addition. However, then your K becomes negative. And then it's okay. You have a negative K, but you do addition, so it's still positive negative feedback. The reason we do this is that we can use our original framework right away. Okay, so it really doesn't matter how you look at it, but you need to be consistent in everything. You will get the same result. Okay, so for those who will just look at the slide, I decided to change it a little bit because those people are not listening to our discussion. So I decided to use the other direction, 0 minus V divided by I equals to RF plus 1 over GM. It's exactly the same as what you define, right? So based on this, what is I? I is approximately equals to, yeah, negative V
over RF plus 1 over.
negative V divided by RF plus 1 over GM, 1, right? Now, however, should RF be small or large if you try to design a good circuit? Why?
What measure is?
Can we go back to the purpose of this feedback? You're right, it needs to be large. Huh? Okay, very good. One is that he said you try to sense the voltage, the RF need to be large. Excellent. Or can you look at from the output perspective? What does it do as the output of the feedback?
Trying to track current
Subject.
input by the feedback.
So it is a source of current. It's a current source. Yeah, a good current source need to be infinite impedance. So very lucky, everything is consistent. Just one resistor, I make it large, I fulfill that I'm a good voltage sensor and I am a good current source, right? And how about 1 over GM? Small or large? Small, yeah. So I try to make my RF large, GM is small, then this is just approximately equal to negative V divided by RF. Okay, so what is the feedback factor? K. Again, very careful. Minus 1 over RF. Okay, so if you never tried this before, you won't be able to imagine, wow, this is negative 1 over RF, which is the feedback factor. Okay, but it's so simple, negative 1 over RF. So let me see. I don't have A, B, C, D. Let me continue from here. Sorry for that, right? And then E from previous line. What is the closed loop gain of this circuit? Right? Maybe I should just do RL. What's the closed loop gain? Maybe you forgot, right? Take a look. What's the closed loop gain? Okay. You say it's a RO divided by 1 plus K RO. Right? Let's do it carefully. What is RO in this case? Are you able to find it? Very messy of APC. Negative GM2, RD1, RD2, right? The total forward gain, right? So let me write it here. Negative GM2, RD1, RD2. And then let me also write the RO first. GM2, RD1, RD2. Okay. What is K? Thank you. As for those who cannot see it, K, negative 1 over RF. I will spend a lot of time to derive it. Negative 1 over RF. It is nice. Two negative make positive. So it's still a negative feedback, right? Because this is the loop gain. I mean, not, is it the loop gain? So then I get negative GM1, GM2, RD1, RD2 divided by 1 plus GM2 RD1 RD2 divided by RF. Okay. What I'm doing is just combine them, that's it. The whole thing is still negative. It still works as what we want before, like a common source amplifier, right? But then the gain is reduced. So when the K times A is much larger than 1, what do we get? It becomes RF. Right? When this term is much larger than 1, this is gone. And then I can cancel GM2, RD1, RD2. Then RF go to the top. So I use RF to control the gain. So if my RF is large, then I have a pretty large gain, right? Which again is good. I want to have a large RF and at the same time have a correct input-output impedance. Yeah. Thank you. Very, very careful. Minus RF. Right? Should be minus RF. So any questions? So that will conclude our feedback, right? Really try to understand what I'm talking about. This is a very important hint for your final. Understand everything. Do not make mistake. Do not make the wrong sign, okay? So we can continue for current feedback, current voltage feedback. For this type of detail, we may test, but we won't go to this type of detail. If you're interested, take a look. Methodology is the same. But very importantly is that we assume ideal feedback network. What is the meaning of ideal feedback network? Can you tell me? What is the meaning that this is ideal? No rules, but on the other hand, we care more about, he said infinite, about the impedance. Okay, so depends on the situation. Like voltage current feedback, we want to have infinite input impedance, infinite output impedance, right? For others, they are different. Some want to be zero, some want to be infinite. Okay, that is the meaning of ideal. But in reality, that is not the case. For example, the RF is not infinite. And if that is the case, then this equation is not valid anymore. But maybe if you close to ideal, it's still approximately correct, which is good, right? Maybe 5% off, 10% off, that is good enough, right? You can use your brain to get 10% off from the computer simulation. That is very good, right? Otherwise, then you have some special equation, which is mentioned in the textbook. Again, in the future, when you see this situation, go back to the textbook. You trust it. I mean, textbook, I went through already, mostly no typo, right? And people use it. Use that equation, use Mathematica to help, or MATLAB to do some calculation to verify what's going on, okay? So that's it, right? So we need to have a large R in our, okay. All right, so let's move forward to the next topic.